Welcome to the second lecture and exercises for the introduction to rodos. In the last week, we learned about rodos threads. We have implemented our own threads. We have played around with the priorities in order to see how the scheduling works. And we also had some timing properties. So we used the time loop in order to have correct timings, the execution timings, and so on. We also had several threads running in parallel to see how they run in parallel. But in real world applications, the threads usually do not just live next to each other without having a dependency on each other. Usually you have some exchange of data, for example. So, for example, one thread is producing some data, reading from a sensor, for example. One might process the data and another one might output some data. And those threads need to interchange data. So there we need some inter-thread communication. There are two purposes for this. One is that I just mentioned, exchange data, and the other one is to synchronize threads. So especially if they depend one of the other, then we have to provide some synchronization between the two threads. For example, the second one should run only if the first one is finished with their calculation, for example. And in order to achieve this inter-thread communication, there are different approaches that we want to have a look at today. Our first approach that we have a look today is a quite simple one. So basically we don't need to learn anything new. We just manually define when a thread is suspended and when a thread resumes. So let's just switch to the virtual machine. In our example, we want to have two threads. One thread is producing some data and one thread is consuming some data. So let's start with the consuming thread. We are going to implement our own thread. So just say class consumer thread. Static thread. Which consumes some data. In this case, we have to save the data that should be exchanged somewhere. We just do it very, very simple. Maybe you will do it on the real world application differently, but we just keep this example very simple. So we have some value that we want to exchange. We just keep this value global so that other threads can access it. That means we have the consumer thread that every time new data is available, it should process the data. In our case, it's just printing the data. Therefore, we just say print consuming and the value. And as I have just said, we have to wait for new values to come. And what we follow with this suspend resume approach is that the consumer thread suspends itself and the producer thread is just waking up the consuming thread every time new data is available. So first we have to wait until new data is available, which means until this consuming thread is resumed. So we just wait forever because we don't know when new data will be available. And this shouldn't be only done once. We want to do this all the time. This is why we put this into a while loop, an infinite loop. So just creating an instance of this thread, consumer thread. So that's for our consumer thread. So let's go on and implement our producer thread. So basically I'm just going to copy this consumer thread here and just change everything. So we have the producer thread. So changing it down here as well. So instead of consuming, we want to produce some data. I'm just removing this one and clearing that one as well, so that we have a clean thread. So what we do, we produce some data. In our case, we just keep it very simple. We have a value that should be incremented every time new data is produced. Here we need some timing. So if we do it in an infinite loop without some timing, it is just very fast. We just want to keep it a little bit slow in order to see the synchronization that we have between those two threads. So I'm introducing this time loop that produces every 2 seconds a new value. So what it does is it increments the value and sets the value within the consumer thread. So this value is overwritten, and after that is done, we can resume our consumer thread. So that's it. So every 2 seconds we increment our value. The value is written to the consumer thread and the consumer thread is resumed, which means that this function here returns the value is consumed, so just print it here, and then the consumer thread here again enters this add function and waits until the next value is produced. So just let's run it. So you see exactly what we wanted to have. We see consuming every 2 seconds, and this printing is only done in the consuming thread. You see, by this you see that it works as expected. So we have a synchronization between those two threads. So we have the internal synchronization, the producer thread, which synchronizes the consumer thread. So this is the very simple approach, the suspend resume approach. But as you might imagined, this only works if you have 2 threads very well. If you have 3 threads, it might be a bit complicated because, for example, if you have 2 producer threads that are overwriting the same value before resuming, some data gets missed. Some data won't get consumed in the consumer thread. So that would not work in that case. For those cases, we have more elaborated mechanisms. For example, the communication middleware, which we will get to know in the next week. So this was the first approach that I wanted to present to you. So let's go back to the slides. There's one use case which is very suitable for this approach. For example, if you want to handle interrupts that provide some data. So for example, we have a interrupt service routine that is called every time new data gets available. For example, we have some input device, some modem, some bus, something like that. And this interrupt service routine just sets the data. So it reads the data from the device, for example, sets the data to the consumer thread and resumes the consumer thread. This is very good to have only little code in the interrupt service routine. So that means that rodos is not interrupted for a very long time. In this case, we just push the data to a thread, and the thread is scheduled according to its priority. That means that all high priority tasks that have a higher priority can be executed in the meantime by rodos. If you do the handling all in the interrupt service routine, no other thread is able to run. So keep in mind, keep interrupt service routines very short and better delegated to an own thread that you can manage with the timings and with the priority. In the next approach, we're going to use a FIFO. So rodos already comes with a FIFO class that you can use for exchanging data between different threads. The idea here is that we instantiate a FIFO object, and both threads, or all the threads that want to communicate with each other, just put data into the FIFO and read data from the FIFO. The FIFO class is very simple. It is a templated class which defines the data type and the length of the FIFO, and you have different simple methods. The most important ones here are the put and the get method. If you want to put data into a FIFO, just call this put method. There is only one parameter, which is the value that should be stored into the FIFO. The type is the type that you specified in the template parameter. And we have a return value of the type Boolean, which means that this method returns true if the value has been stored into the FIFO, so there was space left. If the FIFO is already full and therefore there is no space to save the value into the FIFO, then this method returns false. The get method works similarly. So you also have a parameter, but this parameter you see is a reference which is not const. The reason for this is that the value of the variable that you pass to the invocation of this method is overridden with the value that you read from the FIFO. So if you read data from the FIFO, pass a variable, and its value is just overridden with the data. And the get method also returns a Boolean value, which returns true if new data is available and the data has been written to the parameter variable, and false if the FIFO is empty and therefore there is no data to be written from the FIFO. In this case, the variable is not touched at all. So, and as I've just mentioned, there are other useful methods. Just have a look at the header file to get to know them. Okay, so let's try it in action. I'm going to switch back to the virtual machine. Okay, so let's change our current example, so the suspend resume example, to use the FIFO. First, I'm going to introduce the FIFO object. So this is quite simple. We have our FIFO class from rodos, and there we define the data type and the length of the FIFO. We have a FIFO that can store 8 integer values. So then that means we don't need this variable anymore for the consumer thread, and the producer thread just saves the value into the FIFO. FIFO.put and the value. And in order to make it more clear, I'm just changing the period time to 1 second. Okay, so that's for the producer thread. Let's go to the consumer thread. There we're going to introduce also some time loop in order to make it more clear. Here we are waiting for some time. So we are waiting for 5 seconds. And then we are reading the FIFO twice a second. So at 500 milliseconds. The idea is that we just wait the producer to fill up the FIFO a little bit and read it then in a faster pace. So that makes it more clear how the FIFO works. That means we don't need this add anymore. We need to read the value from the FIFO. And if you remember from the slides, for the get method, you have to pass a variable which is overridden with a new value. And therefore we need a local variable here. And then we are going to request the new data. So FIFO.get. So, okay. But what happens if the FIFO is empty, if we don't have new values? We have to check for that. So we are going to introduce an if clause that prints only if new data has been read from the FIFO. That means if this get method returns true. In the case if there is no new data, we are just printing that there is no new data, just to make the usage of the FIFO more clear. No data. Okay, just let's execute it. The consumer thread is waiting for 5 seconds and starting the consuming. So, okay, what you see here, in the 5 seconds in which the consuming thread waits for starting, the producer thread already started filling up the FIFO. That means as soon as the consumer thread starts after 5 seconds, it can read new data every 500 milliseconds. This is the reason why it has read the values very fast here. But after some time, the FIFO gets empty because the FIFO is filled with 1 value per second, but is read with 2 values per second. That means that there is a point in time where the consumer reads a new data only every second time. So this is how the FIFO works. So you're creating an instance of the FIFO, which is accessed by all the threads that want to participate into the communication here. And on the one side, you can just put data into the FIFO, and on the other side, you can get data from the FIFO. But as you might have noticed, we don't have time synchronization between those two threads. So both have their own time synchronization in hand by using, for example, a time loop. But there's a way to do implicit time synchronization between the threads that use the same semaphore. This can be done with a synchronized FIFO. So the synchronized FIFO is just an extension of the normal FIFO that we have just learned, but it introduces some blocking methods. Blocking methods means that the calling thread can be suspended at this point and resumed later. Those two methods are called sync put and sync get. The signature of those methods has changed a little bit compared to the non-sync variants. So both methods have an additional parameter that is called timeout. It has a default value of end of time. That means it could wait forever if it's not resumed otherwise. The difference in the behavior is here that if the FIFO is full, so if you want to put data into the FIFO which is already full, the FIFO suspends the calling thread until either the timeout has reached or the FIFO has been read, and which makes space available to put the data into the FIFO. So that means in the default way, with the default value, this put method suspends forever until some data has been read from the FIFO. And the same goes for the sync get. So if you want to read data from the FIFO, which is already empty, there is no data to read from. In this case, the method suspends the calling thread until the timeout is reached, for example, end of time, or new data has been put into the FIFO. So let's change our application to use the synchronized FIFO. So we need to use the different class here, which is called the sync FIFO. And we need to use the other methods, the sync methods. So that means for the producer, we are using this sync put. In this case, we just leave the timeout as end of time. So it's not important in our example here. And on the other side, we want to make use of the synchronization mechanism in order to get rid of our manual synchronization here. So what we want to do is we want to use the sync get also with the end of time timeout. And we can just change this to an endless loop without any timing. What we have here now is the sync get is waiting until new data is available. And it's immediately consumed after that. So just let's try it. So you see, the consuming happens as soon as new data becomes available from the producer. Stopping it. So new data is produced every second, which leads to new data in the FIFO. And as soon as new data has been put into the FIFO, this thread is resumed at this point. It's consuming the data and it's going back, reading for new data, but there is not new data. It has to wait for this 1 second until new data becomes available. And you see, we have perfect synchronization in time and we just get the value passed. So this makes it very flexible to use. This makes it very useful to use because we have both. We have data exchange and synchronization. FIFO store a number of elements, but not in every case it is useful to have a list of values one by one. That means you have to read them and process them sequentially. There are cases where you want to only process the latest value. For example, if you have some sensor value, for example, the temperature, you might only be interested in the latest value and not in history of values if you have not processed every value already. In this case, you can use the COM buffer instead of the FIFO. The interface of the COM buffer is similar. So we have a put method and we have a get method, which allows you to put data into the COM buffer or read data from the COM buffer. That means if you read data, the latest put data is returned. So this parameter variable is overridden. You won't get a return value. So those methods are void. So you always can put data and can retrieve data from that. Maybe there are some cases where you only want to process data that is new. So you don't want to process old data because it doesn't change anything if the read data have not changed. In this case, you can use this method down here. So get only if new data. That means that the variable that you pass to the call of the function of the method is only overridden if there is new data. And if new data was available and the value has been overridden, then this method returns true. Otherwise, it returns false and the variable will not be touched. Let us implement this in the virtual machine. So instead of using the FIFO, we are using the COM buffer, which of course does not have the length defined here. So the only template parameter that it requires is the data type that should be saved here. And just let's rename it to make it more clear that it's not a buffer. Okay, so I'm just deleting this one. The producer does not need to be changed very much. We can just say buffer.put and we read the buffer. In contrast to the sync FIFO, we don't have a synchronization mechanism here in the COM buffer. So we don't have a method that suspends the calling thread. Similar to the normal FIFO, so not the sync FIFO, but the normal FIFO, we have to do our own timing management here. So in this case, we also use a time loop again, waiting for some time at 1200 milliseconds. And we read the data every 500 milliseconds, which means twice a second. Okay, now we again need a local variable. I just call it value. And here we can call the get method. So get basically works the same as in the FIFO, but I just want to show you how to use this fancy get only if new data method. So that means that we can check the return value. So if the return value is true, we have received a new value, and that means that this variable has been overwritten with a new value. We just print this new value here, value. And in the other case, if we don't have received a new value, I just print no new value. Okay. So let's run it. So we see every second a new value is generated and put into the COM buffer. And every 500 milliseconds we read the COM buffer. And if we have a new data, we print the new data, which is done here. And if we don't have a new data, which is the case for every second request here, we print no new data, no new value. So the difference to the FIFO is that we have only one value on the COM buffer. So in the FIFO, if the producer produces the new values faster than the consumer consumes them, then they get lined up and they can be read one after the other. In the COM buffer, the producer would just overwrite the same value again and again before it is read from the consumer. That means there is a chance that you don't consume some data that has been overwritten in the meantime. But dependent on the use case, that might be what you intended to. The next element I'm going to show you is the semaphore. The semaphore suspends threads for different purposes. One are mutexes, that means mutual exclusives. One example, and this is what I'm going to show you right now, is if you want to access the same device or the same variable and you want to make sure that only one thread can use it at a time. then you can use semaphores as a mutex mutual exclusive for this device or this variable. The second purpose is signaling. You can give signals from one thread to the other thread in order to resume or to suspend the thread. So the idea behind the semaphore is that threads enter and leave semaphores. So locks or unlocks the semaphores. That means every semaphore can be entered only once or only locked once. That means if the first thread enters the semaphores, all other threads that also want to enter the semaphores are suspended until the first one leaves the semaphore again. Then the next thread gets the chance to execute further. A simple example is this one. This is what I'm going to show you. We have two threads that want to access a device or an output device, for example, and the first thread intends to write ABC to the output device. The second thread intends to write 1, 2, 3 to the output device. We just assume both threads have the same priority. That means they are scheduled in a round-robin manner. That means they are executed in their leaving. So both are executed switching from one thread to the other thread. Consequently, the output can be scrambled. For example, the first thread writes an A, the second thread writes in 1 and 2, the first thread again writes a B, the second a 3, and the first again a C. And if you are a receiver on the other side of the device, you just receive A2, 1, 2, B, 3, C. The receiver doesn't understand anything. So it's just garbage that it receives. If we make sure that the first thread prints to the output and then the second one, that would work maybe for the receiver. So we have to make sure that only one thread is printing at a given time. And this is where semaphores come into play. So that means in this case, every thread enters a semaphore before accessing the output device and leaves the semaphore after accessing the output device. In this case, it would work like this. So the first thread is entering the semaphore. It is green, so it can further execute its code and access the output device. In the meantime, the thread 2 might be executed and might also enter the semaphore. But as the semaphore is already entered, the thread 2 is suspended. So this is why it's red here. So the second thread is suspended until the first one leaves the semaphore. So after that, the thread 1 is finished with using the output, maybe has written its ABC. After that, it leaves the semaphore. So the semaphore is not in use anymore. So that means that the semaphore can activate the second thread that is waiting to be activated, and after that it can access the output. And after accessing the output, it also leaves the semaphore. Okay, so this is the basic principle of semaphores. Let's get our hands dirty and try it in the virtual machine. So I already prepared two threads, the first thread and the second thread. Both do nothing for now. What we want to do, similar to the example right now, the first one should print A, B, C, and the second thread should print 1, 2, 3. Okay, so just to have it running again and again, over and over, we just use a time loop here. So both shall start with the first second and run every second. So I just copy it to the other one as well, so that just ensures that they are executed at the same time here. So then we introduce our printing. A, B, C. And 1, 2, 3. So why do I need to do 3 printfs here and not only 1? So it has 2 reasons. The first one is that the printf itself is already protected by a semaphore, so we won't get the problem with when we use printf. So printf is always safe. And the second one is that we can call the scheduler manually, because we have some time slices where the first thread runs and the second thread runs, and we cannot make sure that in the meantime the scheduler runs in order to switch the threads. With calling yield, we just make sure that this happens. Okay, maybe we should also add some new line here at the end. Okay, so what happens if we execute it this way? We see it's totally scrambled, and it's also not deterministic. So we have 1A, 2B, 3C, or A1, B2, C3, and so on. It's not that what we want to show. What we have in mind here is that we, similar to the example in the slides, we want to have ABC printed first, and then 1, 2, 3 printed after that, or first 1, 2, 3 and then ABC, but not scrambled together. Therefore, we introduce a semaphore. Just create an instance, that's it. No parameters required here at all. Then we enter the semaphore, and we leave the semaphore after that. And we do the same for the second thread as well. So semaphore enter and semaphore leave. Okay. So, and we see it works as expected. So ABC and 1, 2, 3 are not mixed up. So that means when the first thread enters the semaphore first, then all commands here are executed before it leaves the semaphore. And in the meantime, the second one might want to enter the semaphore, but as long as the first one did not leave the semaphore, this thread is suspended at this place. So this method here returns only if all other threads have left the semaphore. Maybe from other programming languages or the standard library, you also might know semaphore guards. We have something similar in rodos which you can use. So we have this macro here, protect in scope, where you can pass a semaphore instance. What this macro does is it immediately enters the semaphore and leaves the semaphore as soon as the current scope, so between the scope is defined here between those curly braces, as soon as this scope is left. So in this case, it automatically leaves the semaphore. This might not be very obvious here in this small example. What is the benefit of this? For example, you have several if conditions or switch case constructs where you have different places where you return from a function, for example. If you don't use this product and scope, you really have to make sure that at every place you finally leave the semaphore. And this is something you could forget if you do it manually. But if you use this product and scope, there is no way to forget to leave the semaphore. So if it's possible, just use this macro. So this was it for today with the second lecture and exercise for Introduction to Rodos. We have learned today about inter-thread communication and synchronization. We have learned about the suspend resume pattern. We have learned about FIFO, the sync FIFO, the COM buffer, and finally how to use the semaphores. At the end, I have an exercise for you. So your task is to create 3 threads and 3 FIFOs. You see on the left side here how the threads and FIFOs are connected. So the first thread puts data into the first FIFO and reads data from the third FIFO. The second thread reads data from the first FIFO and puts data into the second FIFO, and so on. So basically we have a circle that is built up here. Each time a thread reads new data from a FIFO, it shall print the value that it has received. So it's an integer value together with the thread's name. It shall increment the value by 1 and forward the value to the other FIFO. That means the second thread reads a value from the first FIFO, prints it, increments it, and puts it, the incremented value, to the second FIFO, and so on. So as you can see, the data will circle around and it will be incremented 1 by 1 in each step. So in order to kick off this circle forwarding, one of the threads shall start the process by putting the value 1 to a FIFO. For example, the thread 1 shall put at the beginning, at the start of the program, a 1 to this, and then this value will circle around. So, if you have any question, just ask me in the Q&A session or write me an email. Okay. Good luck and have fun with the exercise.